Moment distribution method. Introduction. This method, developed by Professor Hardy Cross in 1932, it solves for the joint moments in continuous beams and rigid frames by successive approximation. In the moment distribution method, initially the structure is rigidly fixed at every joint or support. The fixed end moments are calculated for any loading under consideration. Subsequently, one joint at a time is then released. When the moment is released at the joint moment becomes unbalanced. Carryover moment. It is defined as the moment induced at the fixed end of a beam by the action of the moment applied at the other end. In this diagram, fixed support, which is the moment at A and a reaction at Y, and a ruler, moment at B, and the direction of the reaction is downward. And we presume that both ends are fixed. The formula, moment of A is equal to negative 1/2 of moment at B. Thus, the moment applied at the ruler end carries over to the fixed end a moment that is half the amount, and it is in opposite sign. Beam stiffness. Beam stiffness is the moment required to produce unit rotation at the simply supported end of a beam, the other end being rigidly fixed. Moment at B is equal to beam stiffness K, and the absolute of K is equal to 4 EI all over L. And for constant E, which means we have the constant value for modulus of elasticity, relative K is equal to I, the moment of inertia, all over L, or the span. And we have the modified K. For hinge and ruler ends, multiply K by 3/4 to eliminate further distribution of moment on that support. Fixed end moments, or FEM. Assume that each span of continuous beam to be fully restrained against rotation. Then, fixed end moments at the ends, its members are computed. And for the sign convention, counterclockwise moments acting on the beam are considered to be positive, and clockwise moments acting on the beam are considered negative. This implies that clockwise reaction at the joint is positive and counterclockwise reaction at the joint is negative. And for fixed end moments, or FEM, types of load have the value for end moments and the actual and the used sign. And for the first diagram, we have a concentrated load at distance A from fixed support A and a distance B from point B. And for the end moments, moment at A is equal to negative of P, the load or the concentrated load, times A multiplied by B squared all over the total length, which is from A to B, which is L squared. The fixed end moment at AB is equal to negative PAB squared all over L squared. And for moment at B, it is equal to negative PA squared B all over L squared, or the fixed end moment of BA is equal to the opposite sign, which is positive PA squared B all over L squared. And for the second diagram, we have a concentrated load at mid-span, which means we have L over 2 at A and L over 2 at point B, and a distance of AB or L. And for the end moments at A, it is equal to negative PL over 8, and because it is concentrated at midspan, moment at B is also negative PL over 8. And the fixed end moment at AB is negative PL over 8, while the fixed end moment at BA is the opposite sign, or plus PL over 8. And for the third diagram, we have a uniform load, which is W, and it is from A to B at a distance L. And the end moments at A is equal to negative WL squared all over 12. While MB, or the moment at B, it is also equal to negative WL squared all over 8. And the fixed end moment at AB is equal to negative WL squared over 12. And the opposite value or sign for fixed end moment at BA is equal to positive WL squared over 12. And for the fourth diagram, we have a uniform load at half of the span from point B. Moment at A is equal to negative 5 WL squared all over 192, while moment at B, it is equal to negative 11 WL squared all over 192. And for the end moments to be used, FEM at AB is equal to negative 5 WL squared over 192, and FEM of BA is positive 11 WL squared all over 192. Additional load, a varying load from A to B with W at point B. The end moments, moment at A, it is equal to negative WL squared all over 30, while MB or moment at B is equal to negative WL squared all over 12. And for the sign, FEM of AB is equal to negative WL squared all over 30, and FEM of BA, it is equal to WL squared all over 20. And for a triangular load at a midspan of W, we have moment at A is equals to negative 5 WL squared all over 96, while moment at B is equals to negative 5 W all over or L squared all over 96, which means they have the same value. For the fixed and moment at AB, it is equals to negative 5 WL squared all over 96, while FEM of BA, it is equal to positive WL squared all over 96. For the next diagram, we have a moment at distance A from point A or distance small b at point B. And the formula for end moments, we have moment at A is equals to mb all over L multiplied by 3a all over L minus 1, close parenthesis. And for moment at B, negative moment of A, m times A all over L multiplied by 3b all over L minus 1, close parenthesis. Fixed end moment at A is equals to positive moment mb all over L multiplied by 3a all over L minus 1, and fixed end moment at BA is also plus moment times A all over L multiplied by 3b all over L minus 1, and close parenthesis. And for the last diagram, we have a deflection of delta from point B, and the moment at A or the end moments at A is equals to negative 6 EI times delta all over L squared, and the moment at B is equal to 6 EI delta all over L squared. And for the fixed end moment at AB, it is equals to negative 6 EI delta all over L squared, and fixed end moment at BA is also negative 6 EI delta all over L squared. So these are the standard formula for fixed end moments. So we will be using the formula based on the given load. After the fixed end moment, we will find the distribution factor or DF. At the joint, the distribution factor of a member is the ratio of the bending stiffness of the member to the sum of bending stiffness of all the members connected to the joint. DF or the distribution factor is equal to K all over summation of K. In general, the end moments of any two adjacent spans are not equal, creating an unbalanced moment at the joint. Unbalanced moment is then distributed in percentage equal to the distribution factor. However, take note of this, the distribution factor is equal to 0 for fixed end, while the distribution factor is equal to 1 for hinge or ruler end. Example: From the beam shown, which of the following gives the fixed end moment at B due to the concentrated load in kilonewton meter? Number 2. Which of the following most nearly gives the distribution factor at B for the member AB in percentage? And which of the following most nearly gives the moment at B? In this diagram, three supports. At point A is a hinge, at point B is a ruler, and point C is also a ruler. And this is the indeterminate beam, which means more than three supports. And from A to B, we have a concentrated load of 3 kilonewton at a distance 5 meters from A and 3 meters distance from B. And from B to C, a uniform load of 4 kilonewton per meter with a distance or span at 5 meters. And we will determine the fixed end moment at B based on the concentrated load. And then, number 2, we will find the distribution factor at B for the member AB in percentage. Number 3, we will find the moment at point B using the moment distribution method. So let's find first the fixed end moment or the FEM at B. FEM at B. And based on the diagram, based on the formula at moment at B, it is equal to positive PA squared B all over L squared. And at AB, 5 meters, which is equivalent to A, 3 meters B, and the total length of AB is equal to L, and P is the concentrated load, which is 3 kilonewton. And then we substitute the value plus P, which is 3 kilonewton, and multiplied by A squared, which is 5 squared, and then multiplied by B, which is 3, and then divided by L squared, which is 8 meters squared. And moment at B, or the fixed end moment at B, is equal to plus 3 times 5 squared times 3 all over 8 squared. The value, it is equivalent to plus 3.52 kilonewton meter. So this is the fixed end moment at B based on the concentrated load of 3 kilonewton. Next, number 2, which of the following most nearly gives the distribution factor at B for the member AB in percentage? And we will find first the K, or this relative stiffness factor, which is K is equals to I over L. KAB is equal to I, and the distance of AB is 8 meters, while KBC, the next span, and the distance is 5, so I over 5. And to find the distribution factor, DF is equal to K all over summation of force, or summation of K of all K's. And DFBA, DFBA is equal to K of AB all over K of AB plus K of BC. And we substitute K of AB is I over 8, and we divide by KAB, which is I over 8, plus K of BC, which is I over 5. BA is equal to I over 8, and this is the least common denominator is 8 times 5, or 40. This is 40, and this is 5I plus 8I. and I over 8. Then the reciprocal of 5i plus 8i or 13i over 40. This will be 40 all over 13i. Cancel out I. That's 40 all over 8 times 13. And df of BA is equal to 0.38, or in percentage, that's 38%. And that's the distribution factor at B for the member AB, and it is in percentage. Next, we will find the moment at B using the distribution factor table for the distribution factor, and this is the joint. This is A, and this is the center at B, and C. We'll have the value for DF, fixed end moment, FEM, and then the balance, and then the carryover. But before that, we will find first the fixed end moment at BC. Fixed end moment at BC, FEM at BC, and the formula for a uniform load for fixed end moment, MBC is equal to negative WL squared all over 12. And the value for W, we have 4 kilonewton per meter. That's 4, negative 4 times L, that's 5 squared all over 12. And BC is equals to negative 8.33 kilonewton meter. MCB is also positive WL squared all over 12. 4 times 5 squared all over 12, and it is also 8.33 kilonewton meter, and that's positive. So we have now MBC and MCB, while moment or fixed end moment at AB using the formula based on the concentrated load is equal to negative PAB squared all over L squared, and negative value of P, which is 3 times A, that's 5, and B, 3 squared all over 8 squared, and MAB is equal to negative 2.11 kilonewton meter, while MBA, which is the fixed end moment, BA, the question at 1, the fixed end moment at B, and the value for moment at BA, that's positive 352 kilonewton meter. So we have now the fixed end moment values. We will try to apply the distribution factor at joint A, a hinge. Therefore, dF is equal to 1. Next, at BA, the value for the distribution factor at B for the member AB, previously at number 2, we have the value which is 0.38 or 38%. So that's 0.38. And the ruler or the distribution factor for a ruler is also 1. So therefore, 1 minus 0.38 is equal to 0.62, and that's the distribution factor for BC, and this will be 0.62, a total of 1.0. And at point or joint C, a ruler, the df factor or the distribution factor for a ruler is also 1. Fixed end moment at AB, negative 2.11, at BA, 3.52 positive, so that's 3.52, and BC, the value for BC, that's negative 8.33, and value for CB, that's positive 8.33. 8.33. We will multiply the distribution factor to the value of fixed end moment. At joint A, we have a factor of 1 multiplied by negative 2.1, and the sign should be changed from a negative sign to a positive sign. Final moment at joint A, which is the moment is equal to 0. So 1 times negative 2.1, 1 is equal to positive 2.11. The fixed end moment of joint B, we have two values, 3.52 at BA and negative 8.33 at BC. So let's check. At joint B, 8.33 plus 3.52, and the value, that's negative 4.1. That's the fixed end moment at B. And we will distribute that based on the distribution factor of BA and distribution factor of BC, which means we will multiply and change the sign. So negative 4.81 multiplied by 0.38, and the value, that's 1.83, and we change the sign from negative to positive. 4.81 multiplied by the value for BC, which is this distribution factor of 0.62, and the value is equivalent to 2.98. If we add up 1.83 and 2.98, the total should be 4.81, and equate that in order for us to balance the equation. So the value for BA, that's 1.83, and it's positive. So we will put 1.83, and for BC, that's 2.98, and that's positive. At joint C, we have the distribution factor of 1 and FEM of 8.33. So 8.33 times 1, and we have the value, that's, and change the sign, so that's 8.33. And the carryover moment, that's MA is equals to negative 1/2 of MB. And at joint A, 2.11 carryover at joint B of BA. So the carryover from the balance, that's 2.11, and we'll multiply by 1/2 of the value, which is equivalent to or equal to 1.06. And this is the carryover from A to B. That's 1.06. From joint C, we have a negative 8.33, and we will be using the carryover moment, the value 8.33, and multiplied by 1/2, and equivalent to negative sign 4.17. So negative 8.33 divided by 2, that's 4.17. And this will be carry over to BC. And this is negative 4.17. After this, we will have another balance. So balance. We can use balance 2 or 3 times at most, and we can have the final value for moment. And again, using the distribution factor and the carryover value, so 1.06 minus 4.17, and the value is equal to negative 3.13. And this will be the value to be multiplied by the distribution factor of BA and BC. So that's negative 3.13 multiplied by 0.38 and equivalent to 1 point, and change the sign from negative to positive. So that's 1.18, while 3.13 multiplied by 0.62 and the value for BC, which is equivalent to 1.93. So that's 1.93. Two values will be put at the balance, which is at BA, that's 1.18, and at BC, that's positive 1.93. And we don't have the value for the balance for A because the value is equal to 0. And at C, the value is also equal to 0. And we will now have the final moment value. So final moment at joint A, which is a hinge, therefore the value or the moment is 0. There's no moment at joint A because it is a hinge. At joint C, it is a ruler. Therefore, the moment is also 0. But at joint B, we will have the internal moment at point B. And at BA, we will sum up everything from the fixed end moment until the last balance value. So 3.52 plus 1.83 plus 1.06 and 1.18. And that's the final moment at BA. So let's check. 3.52 plus 1.83 plus 1.06 plus 1.18. And that value is positive 7.59. We will not add the value 0.38 and 0.62 because that's the factor or the distribution factor. We will only add all the moment value from fixed end moment, balance, carryover moment, and the another balance, and that's the total value. And it should be that the moment at BC is closely same value at BA. However, the sign should be opposite sign. So let's check negative 8.33 plus 2.98 minus 4.17 plus 1.93. That's negative 7.59. And this is the final moment at moment A or moment BA, that's 7.59, and moment BC is the opposite sign but the same value, that's negative 7.59. And we have now the value for moment at B or the internal moment at B. So this is the answer.